Welcome to the fourth day of Summer General Physics. On this day, we'll be looking at more examples of projectile motion. We'll be looking at motion in a circle and something called centripetal acceleration. And we'll also be looking at relative motion, that is, motion that is observed by more than one observer that may be traveling with respect to each other. So in this first video, we'll continue to look at some examples of projectile motion. So first off, here's a question for you. As a projectile moves in a parabolic path, the velocity and acceleration vectors are perpendicular to each other where? Is it everywhere along the path? At just the peak? Nowhere? Or do we not have enough information to determine the answer to this question? So please pause the video here and give this some thought and select your answer. Okay, so now that you've selected an answer, let's take a look at this type of motion and these options. So if an object is moving in a parabolic path, then that means its motion looks something like this. You have a parabola that the object is traveling along. The acceleration, what direction is the acceleration? Well, we know that there's no acceleration in the x direction. In the horizontal direction, there's no force and there's no acceleration. The object travels with a constant velocity in the horizontal direction. In the vertical direction, however, the object is experiencing free fall. Gravity is acting on it, slowing it in the horizontal or in the vertical direction as it moves upward, and then speeding it up in the vertical direction as it moves downward. So all of the acceleration takes place in the vertical direction. In the vertical direction we have free fall, and so the acceleration is always downward and has a magnitude of 9.8 meters per second squared. And that's true at any point along the path for the projectile. So it's always downward and always 9.8 meters per second squared. Now what about the velocity vector? Well, the velocity vector points in the direction of motion. So at this point, the velocity vector would point like this. At this point, the velocity vector points like this. At the top, the very top, the velocity vector points in the horizontal direction, because in the vertical direction, the motion has stopped and is turning around. And then we have velocity vectors that look like this on the other side that point mostly downward. So there's only one place where the acceleration vector and the velocity vector are perpendicular, and that is at the peak of the path. So I would want to choose option B. Okay, so here's a second question. How could you throw a projectile so that it has zero speed at the top of its trajectory? So pause the video here and think about these options. Okay, so now that you've selected your response, let's look at these different options. So they are straight upward, 45 degrees above the horizontal, horizontally, or would it not be possible for it to have zero speed at the top of its trajectory? Well, we know that in the vertical direction, there's going to be a point at the top where the velocity in the y direction drops to zero. And in order for the projectile to have zero speed at this location, its velocity in the x direction would also have to be zero. However, if the projectile starts out with any horizontal velocity, that velocity will continue throughout the whole trajectory. So the only way to have zero speed at the top of the trajectory is for the horizontal velocity to be zero, meaning that you'd have to throw the projectile straight upward. So if you throw it straight upward, it has no velocity in the horizontal direction, and at the peak of the path, the vertical velocity will also drop to zero. So let's take a look at solving another projectile example problem. And this one is a little bit more challenging than the ones we've looked at so far. So in this problem, we can see a picture of the situation, so that's kind of already done for us. And in this picture, a 2-meter tall basketball player is standing on a floor 10 meters from the basket, so we know how far the ball travels horizontally. He shoots the ball at a 40-degree angle with respect to the horizontal, and we want to know the initial speed so that it goes through the hoop without striking the backboard. So it goes perfectly through that hoop, and so when it travels 10 meters in the horizontal direction, it will be 3.05 meters above the floor. And we know the height at which the ball started out as well. All right, so we have a picture of this situation already. So we can start by, as always, the first step is to break the motion up into x and y components. Specifically, we have to break the initial velocity up into x and y components. So let's draw a picture of just that initial velocity. So initially, the velocity with which the basketball player throws the ball is aimed 40 degrees above the horizontal, and its amount is unknown, so I'll just label that V0. So then that means that the initial velocity in the x direction is V0 cosine of 40 degrees. And the initial velocity in the y direction is V0 sine of 40 degrees. So that's the best I can do because I don't know what V0 is, so I'll just keep it as a symbol for now. So then I can write down my equations of motion in the x and in the y direction. In the x direction, the velocity is constant, so I can write down that delta x is equal to the initial velocity in the x direction times time, and I can plug in what I have for my initial velocity in the x direction. That is V0, the total initial velocity, times cosine of 40 degrees times time. So what about in the y direction? So I should write down a list of my knowns in the y direction. So in the y direction, I know that the initial velocity in the y direction is V0 sine of 40. I don't know what V0 is, but I at least know the angle, so that's some information. And I also know the displacement in the y direction. Now remember, displacement, or delta y, is the same thing as the final height minus the initial height. And in this case, the final height is 3.05 meters, and the initial height is 2 meters. So that means that my delta y is going to be a positive 1.05 meters. And let's see, is there anything else that I know about the motion in the y direction? I think that's it for now. Oh, but I remembered one thing I forgot to write down about the motion in the x direction, and that is that in this case, I actually know what delta x is. I know that it's equal to 10 meters. So I do know that 10 meters is equal to V0 cosine 40 times time. So then, what is my unknown that I'm looking for in the y direction? So if I think about this, and if I think about my my equations of motion in the y direction, my free fall equations, now ultimately, of course, the thing that I want to know is the initial speed. I want to know V0. But V0 is in two different places. It's here in the x direction, here in the y direction. But I can't solve this equation for V naught because I don't know time. I don't know what t is. So I think what I should do is actually let my unknown for the moment be time. Because if I can solve for time using my y equations or get some equation for time in terms of y, then I can plug it in terms of x or into my x equation and then hopefully be able to solve for v naught or vice versa. All right, so now that I have my initial velocity and the change in position in the y direction and know that I think I'm aiming for something involving time, then I can take a look at my free fall equations and choose one. And I think I'm going to choose the one that says delta y is equal to v naught y t minus 1/2 gt squared. Because that involves time, it involves the initial velocity, and it involves the change in position, which I do know. All right. So then I will plug in the information that I know about this expression. So let's see, I know that my delta y is 1.05 meters, and I think I'll just plug in what v naught sine theta, that's my v naught y. So I'll rewrite this just a little bit and say that v naught y is the same thing as the initial velocity, the whole initial velocity, times the sine of 40 degrees t minus 1/2 gt squared. Okay, so I know what delta y is. I have my 40-degree angle. I know what g is. I don't know what t is, and I ultimately want to find v naught. So if I look at these two expressions I have, this one for the x direction, this one for the y direction, I see that I have two variables, which are my v naught and t. I have those two unknowns. I know what delta y is, and I have two equations. So I need to combine these somehow, and I would really like to get rid of time because what I really want is an equation that tells me about the initial velocity. So I think what I'll do, the strategy I'll take, is to solve this first equation for the horizontal motion. I'll solve that one for time because it's the simpler of the two, and then I'll plug it into this equation, and then I'll have an equation where my only unknown is the initial velocity. So let's follow that strategy. So here, and I'll go back to using delta x instead of 10 meters just because it'll save me a little bit of writing. So if I solve this equation for time, then time is going to be equal to delta x, which is 10 meters, divided by v naught cosine of 40 degrees. Okay, so then I can take this expression for time and plug it in to these two places for my delta y equation. So then delta y is going to be equal to v naught sine 40 degrees times delta x divided by v naught cosine of 40 degrees minus 1/2 g, and then I take that expression for time, delta x over v naught cosine 40 degrees, and square it. Okay, so next I'll look to see if I can do any simplifications. So one simplification I can see is that I have a v naught in the numerator and the denominator, so those will cancel. And another simplification that I can see is that I have a sine of 40 over the cosine of 40. And if we remember our trig identities, sine over cosine is the same thing as tangent. So I can rewrite this as delta y is equal to tangent of 40 degrees times delta x minus, and then if I expand the squared, I would have g times delta x squared divided by 2, can't forget my 1/2, v naught squared cosine squared 40 degrees. Okay, just a little bit of explanation on the math here. So when I square everything, I have to square everything in the parentheses, so all of these pieces get squared. And a word on notation, cosine squared 40, what that means is you take the cosine of 40 first and then you square it. The reason why we usually write the squared here after the cosine instead of after the 40 degrees is that if we did it after the 40 degrees, it might be confusing. You might think that you need to square the 40 degrees and then take the cosine. But what we actually want to do is take the cosine of 40 first and then square it. All right, so this is a interesting equation, slightly complicated, but I need to remember, what is my goal? My goal is to find my v naught, the initial velocity. That's what the problem's asking for, and that's the only unknown in this equation. I know what delta y is, I know what delta x is, I know what g is, yeah, there's delta x again. Yeah, the only thing I don't know is the v naught squared, so I need to solve for my initial velocity. But it's stuck here in the denominator of this second term. So I think what I'll do is I'll multiply through everything by that initial velocity squared. So if I multiply through everything, that means multiplying each one of the terms by v naught squared. So there's a v naught squared here and a v naught squared here, so that cancels. And now I have two terms with a v naught squared in them. So I need all of my v naught squareds on one side of the equation. So I'll subtract this term from both sides, which will give me v naught squared delta y minus v naught squared times the tangent of 40 degrees times delta x is equal to minus g times delta x squared divided by 2 times the cosine of 40 degrees squared. Okay, so then the next thing I need to do is to factor out a v naught squared from these two terms. So I would have a v naught squared times delta y minus tan 40 degrees delta x equals the same stuff on this side of the equation. And then the last step is going to be to divide through by the stuff in the parentheses. So I get v naught squared all by itself. So v naught squared is going to be equal to minus g delta x squared divided by 2 cosine 40 degrees squared, and then I have to multiply that by, because I'm dividing both sides, by the stuff in the parentheses, delta y minus tan 40 degrees delta x. And then of course I would need to take the square root of both sides. So that was a lot of math, but we can see that we get an expression now for my initial velocity, and it's in terms of all different things that I know. So the last step is just to plug in numbers. So if I do that, and I'll have to erase so I have a clean slate with room to write on, or, well, maybe I have some space here. Let's do it here. All right, so my v naught is going to be equal to the square root of negative 9.8 delta x, which was 10 meters. That gets squared. Then I have in the denominator 2 I have a cosine of 40 degrees squared. And then that multiplies my delta y, which was 1.05 meters, minus tangent of 40 times 10. Okay, so if you put that into your calculator, then you should get an initial velocity which is equal to about 10.7 meters per second. Okay, so this looks complicated, but really it was just a bunch of math. The setting up of the problem involved the same steps as before. You split the initial velocity into x and y components, write down your equation of motion for the x direction, write down your knowns, the equation of motion in the y direction, plug in all the information that you have, and then solve for the unknowns in your problem. So one last equation that we want to consider when dealing with projectile motion is the range equation. And the range equation applies to a very special case of projectile motion. It only applies when the projectile starts and stops at the same height. In other words, when delta y is equal to 0. So if the projectile takes off and lands at exactly the same height, then we can answer the question of how far does it travel with the range equation. And the range equation gives us the range, or the delta x, how far it travels in the horizontal direction. And you can see that the range equation is quite simple. It just involves the initial velocity and the launch angle and g. So there's no need when using the range equation to break the motion up into x and y components. You just have to plug in the total initial velocity and the launch angle. So the range equation is very nice. It's very simple to use, but it can only be used in this special case of the projectile starting and stopping at the same height. Now, another thing that the range equation tells us is it tells us what is the optimal angle to launch an object if you're launching it over level ground, and then the object would start and stop at the same height. So if you're launching over level ground and you want your projectile to go as far as possible, the sign is going to be the biggest when the stuff inside the sign is 90 degrees. But since we're doubling the angle, that means the optimal launch angle is 45 degrees. So we can see that using a projectile motion simulator. And you can see I've given the URL of this projectile motion simulator here in the slide. So let's go take a look at that simulator. So here is the simulator, and it's kind of fun to play with. So you have a cannon, and the cannon can launch projectiles. And as you can see, you can control the kind of projectile, you can control the mass, the diameter, you can make gravity stronger or weaker, and you can also turn on and off air resistance. Now, currently air resistance is off, and so the mass and diameter won't affect the motion. But if you include air resistance, then the mass and diameter, how big your object is and how heavy it is going to matter, because air resistance involves more complicated motion and does depend on how big the object is. So let's try firing this cannon, and currently the angle is 25 degrees. So we can watch our projectile and see how far it travels. We can also measure its distance. So we can measure how far the projectile went. So this is a pretty nifty simulator. We can also change the angle of our cannon and the launch speed. So right now I have it at 25 degrees. I can also go higher than 45 degrees, say 50 degrees, and shoot the cannon. And there I see that the projectile goes a bit further. However, if I make my launch angle for exactly 45 degrees, that's where the projectile goes the furthest. And I have a target here that celebrates when I hit it. And you can move the target around too, so cheating is quite possible. Now this is a pretty fun simulator, as I said, because it not only lets you practice with different speeds and launch angles, but it also allows you to shoot different objects. So instead of a cannon, I can shoot a golf ball or a baseball or a football. So you can see the football get shot out of the cannon. I can also erase former trajectories. But then there are some more whimsical things that can be shot, such as pumpkins and also we can shoot humans and a piano. And things like that. So play around with this. It's a good way to build your physical intuition as to what's going on, and of course it's just plain fun as well. So that concludes this video. In the next video, we will continue to look at more examples of projectile motion. The first example will involve a movie called Speed. And you will see a movie clip that you should watch before continuing on with the next course video so that you have context for the problem. Now, if you're not familiar with the premise behind Speed, Speed was a movie that came out in the 90s. And in this movie, there was a bad guy who put a bomb on a bus full of people, a city bus full of people. But the bomb would only go off if the speed of the bus dropped below 50 miles per hour. So they have to keep the bus going above 50 miles per hour, and there is a problem because there is a gap in the freeway up ahead. So watch and see what happens, and then in the next video we'll do a problem involving that the bus and the gap and what you see in the video.